So, Samuel, you've covered a lot in this book, right? Lots of algorithms.
Yeah, from basic planning to deep reinforcement learning. It's a wide range.
This final chapter, what's the main takeaway?
We're looking at the bigger picture now. Zooming out. Seeing what we've learned so you know where to go next.
Okay, like a roadmap?
Exactly. Plus, there's more to deep reinforcement learning than this book covers. I've mentioned some other agent types too, that I haven't had space for.
So, we've got the basics, but there's a whole universe beyond?
Yeah. And artificial general intelligence, AGI, that's a hot topic, but it's often used to grab attention.
How do you think we should look at AGI?
Focus on the solid concepts. Don't get distracted by the hype around AGI. Humans will keep trying to understand intelligence and automate tasks for sure. And we'll get there, eventually.
But if we can't even train a single agent to play all Atari games.
Right, a single agent can't yet master every game, but we can train a single algorithm for different tasks independently. That's important to remember. It's a process, not an overnight thing.
Okay, so, practical advice for learning more or applying this?
Absolutely. I get tons of questions about applying deep reinforcement learning to custom problems. I do it daily, so I can give tips.
And advice for a career in this field?
Study hard. Keep learning. And don't just study deep reinforcement learning. Look at the bigger picture, What are the foundational concepts? What are the applications?
Sounds good. Any last thoughts before wrapping up?
Keep in mind, we're still at the beginning of this journey. It's exciting, but we need to be cautious about jumping to conclusions. There's a lot more to learn, so keep learning.
So, Samuel, this book covers a lot of deep reinforcement learning, right? What core concepts are in there?
Yeah, most of the fundamentals, from Markov decision processes to cutting-edge actor-critic algorithms. How to train them in complex environments.
Cool. And what wasn't covered?
Well, some advanced topics are out. They aren't needed for many applications.
Okay, but why leave out some crucial bits?
Well, deep reinforcement learning keeps evolving. New algorithms pop up monthly. A single book can't explain everything with high quality.
Gotcha. So, two key methods were omitted, right?
Yep. Model-based deep reinforcement learning and derivative-free optimization methods.
Interesting. Those sound really important. Can you give us a little more insight into why model-based methods matter?
Sure. Model-based approaches try to build a model of the environment. This lets the algorithm predict future outcomes, making training more efficient and stable.
So, they're kind of like a roadmap for the environment?
Exactly. Imagine you're driving. A model helps you visualize the whole road ahead, not just what's immediately in front of you. You can plan a better route.
So, what about derivative-free optimization? Why would that be important?
Traditional optimization uses derivatives to adjust parameters. But some problems don't have clear, usable derivatives. Derivative-free methods tackle these by testing changes. Often, these methods can be simpler and are useful for some environments.
So, this book focuses on a practical approach, covering essential methods for most situations?
Precisely. This allows readers to get hands-on with deep reinforcement learning without getting bogged down in advanced, less commonly used methods.
Right. So the book isn't trying to be a complete encyclopedia, but rather a practical introduction. That makes sense. So, Samuel, you've mentioned value-based, policy-based, and model-based approaches. Can you break down the key differences?
Absolutely. Imagine you're teaching a dog a trick. Value-based is like rewarding good behavior based on expected rewards. Policy-based focuses on directly learning the best action to take in a given situation. Model-based attempts to create a mental model of the environment, so actions become more strategic.
Okay, that's a good starting point. But how does sample efficiency play into this?
Value-based methods often need a lot of data to learn effectively. Policy-based learns the optimal behavior directly from experience, which can be faster. Model-based approaches can use simulated data, reducing reliance on real-world experience. Thus, it's sample efficient.
Interesting. What about computational cost?
Value-based is generally less computationally expensive. Policy-based methods, because of how they work, can require significantly more computing power. Model-based, by creating a model, is usually more demanding computationally.
So, there are trade-offs. How about direct learning?
Value-based has a less direct approach. It focuses on estimating values, not directly learning the best actions. Policy-based and model-based have more direct learning pathways.
And the learned function?
Value-based uses learned functions to evaluate actions. Policy-based methods directly learn the function mapping situations to actions. Model-based creates a function to predict how the environment changes.
So, does one approach always outperform others?
No, it depends entirely on the task. A game with simple rules might benefit from a less computationally intensive approach, like value-based learning. More complex scenarios might favor model-based methods. Some situations are more appropriate to policy-based methods. It's a balancing act.
Makes sense. Thanks, Samuel. This is really helping me understand the complexities of deep reinforcement learning. So, Markov decision processes, right? Crucial to reinforcement learning. Can you break this down for us? What's the basic idea?
Yeah, MDPs are like a roadmap for decision-making in uncertain environments. Think of a game.
Like chess?
Exactly. You have states, like the current board position, actions, like moving a piece, and outcomes, like capturing a piece or getting checkmated.
Right, so these states, actions, and outcomes
form a graph. You start at a state, choose an action, land in a new state. And the whole point is finding the best sequence of actions to reach a desirable outcome.
So, a path through this graph? How does it get better?
That's where the rewards come in. Some actions give better rewards than others. The process learns which actions lead to higher rewards over time.
Rewards? Specific numbers associated with actions?
Exactly. Each action in a state earns a reward. And the MDP finds the policy, the best set of actions to maximize expected reward over time.
Makes sense. But how simple or complicated can these MDPs get?
Well, imagine a robot navigating a maze. Each position is a state. Moving forward, turning left, or turning right are actions. Finding the fastest path to the exit is the goal, which is the policy.
That seems pretty straightforward. But could it get tricky?
Absolutely. The robot might get bumped by other objects or encounter obstacles. That changes the states, the possible actions, and the rewards.
So it's not always a predetermined reward structure.
That's right. You can also have stochastic rewards. The reward isn't always guaranteed. Imagine a slot machine. Pulling a lever can result in a win or nothing. So, the expected reward over a series of actions becomes important.
Okay, so we've got states, actions, rewards. What about observations?
Observations are what the agent sees in a given state. In the maze example, the robot might see walls or open pathways. These observations are crucial for deciding the best action.
So the agent needs to process what it sees in order to decide the best action?
Precisely. Understanding those states, actions, observations, and rewards is key. And the crucial takeaway? Thinking about problems in this way, as an MDP, helps frame complex problems in a tractable way.
How do we practice this?
Think about a problem. Break it down into those components. Start with a simple example, and gradually increase complexity.
Okay, Samuel, so we're talking about representing the frozen lake environment as a Markov decision process, MDP. Can you break down what that means?
Sure. An MDP basically describes a situation where the future depends only on the current state and the action you take.
But isn't the real world, often messy? Like, is that ever really true?
Well, the world can seem non-stationary and non-Markovian, but we can often simplify it. Think about the probability distributions. Do they change in the real world?
Potentially, right? The weather changes or some other thing.
Exactly. Or maybe we just don't have enough data. Sometimes that's the problem. And the state space might be super complex.
So if the history of everything is included in the state, is that even manageable?
Right. Imagine trying to include every single past event. That's a huge state space. The trick is to find a way to summarize all that into manageable states.
So, you're saying we find a way to compress all that information? How do we do that?
That's the art of it. In this model, we use a set of states, a set of actions, a transition function that tells us how likely we are to get to a different state, reward signals, a starting state, a discount factor, and terminal states. It's a simplification.
Interesting. So, the discount factor is important?
Yes. The discount factor reflects how much importance we place on future rewards. A lower discount factor means the future matters less.
So, there's a trade-off between the current and future rewards.
Exactly. And you might think the world is non-Markovian, but if we are careful about how we represent the state, we can get a nice MDP representation.
But how do you deal with uncertainty? Like if you don't know the exact transition probabilities?
That's a good point. We might approximate the probability distributions using data. It's about finding a good enough approximation, and that often works well in practice, in the real world.
That makes a lot of sense. This is a pretty powerful abstraction, though.
Yeah, and it's a valuable technique for using DRL. Fitting your problem into an MDP framework is often a great first step.
Okay, Samuel, so this policy evaluation, it's all about figuring out how good a strategy is, right?
Exactly. We're looking at the always left policy here.
In this SWF environment, that's like a specific game or problem, right?
Yeah, a simulated world. It's important because these are sequential decision problems.
Sequential? Like, one action leads to another?
Precisely. And crucially, there's no uncertainty. We know exactly what will happen with each move. This helps simplify things.
So, the algorithm basically runs through this environment, right?
Yeah, a full state sweep. It's like trying every single possibility.
And these iterations you're mentioning, are those like steps or trials?
Yes, like trials of the policy. Each iteration refines our understanding of how good always left is.
And you said the results converge?
Eventually, we get a complete picture of the value of always choosing left.
How do we know if it's converged?
We look for the Q function to stabilize. Think of it as if the rewards we're getting for always left aren't changing much from one iteration to the next.
So, what's the outcome of this evaluation?
A final state value function, telling us the total predicted reward from choosing always left.
So, the takeaway is we have a final numerical result for the effectiveness of always left?
That's right. We've measured its performance in this world.
And there are broader takeaways. What's the big picture, Samuel?
These methods are simple for specific scenarios, but they're fundamental. They help us evaluate behavior. Evaluating is just as important as trying to improve. Many times, we get so caught up in improvement we neglect how to evaluate correctly. Getting evaluation right often makes improvement much simpler.
That's a good point. I mean, if you don't know how well a policy performs,
then how would you know how to make it better?
So, Samuel, you mentioned tabular reinforcement learning is foundational. Why is that?
It's the bedrock. Think of it like learning to ride a bike. You start with small steps, flat ground, then gentle hills. Tabular RL is the flat ground. It helps you grasp the fundamental concepts of reward, action, and learning without the complexities of giant datasets.
Makes sense. So, these methods are just simpler versions of deep reinforcement learning?
Exactly. DRL has massive state and action spaces. Tabular RL deals with more discrete, manageable ones. This makes it a great stepping stone for grasping the core principles.
You said chapters 5, 6, and 7 are key. Can you elaborate?
Chapter 5 covered evaluating policies, figuring out if a set of actions is working. Chapter 6 focused on optimizing them. Chapter 7 then took us to more advanced techniques. It's like refining your bike handling.
Cool. So, what kinds of algorithms were covered?
Lots. Monte Carlo methods like first visit and every visit. Temporal difference learning. N-step TD and TD lambda. Crucial control methods like SURSA, Q-learning, even double Q-learning. More advanced ones like SURSA, lambda, and Q-lambda, with accumulating and replacing traces. And model-based approaches, like DynaQ.
Wow. That's a lot. How do these algorithms relate?
They build on each other. You start with simpler methods like Monte Carlo. Then you move to TD, a powerful technique, which is often faster. Q-learning is a key building block for more complex agents. You often start with a discrete state space problem and only increase the complexity later. There's a lot of value in not rushing to the deep stuff right away.
Right, a methodical approach. So, these are all fundamental?
Absolutely. Understanding these methods gives you a solid grasp of the ideas behind deep reinforcement learning. You know the underlying mechanics. It's like learning the alphabet before reading a novel, you know?
Helpful. What are common misconceptions about this?
People sometimes think deep reinforcement learning is entirely different. It's not. It's just a more complex version of this core. Complexity is a dimension of the issue. You can get meaningful results with tabular methods. Starting with the simplest approach first is a strong strategy.
So, Samuel, value-based deep reinforcement learning, we're diving deeper. NFQ, DQN, DDQN, these all sound pretty technical. What's the core idea?
Yeah, it's about learning the best action to take in a situation. Think of it like training an AI to play a game. DQN is a foundational method. It learns by trying things, getting rewards, and adjusting its approach over time.
So, like trial and error?
Exactly. But DQN and its improvements are iterative. We start with DQN, then add things like double DQN, which helps reduce overestimation. Dueling architecture helps break down the decision process into parts for better learning. Prioritized experience replay? That's like focusing on the tricky situations.
So, they're all just building on DQN?
Pretty much. Each technique fine-tunes the learning process. For instance, double DQN addresses a common problem in Q learning.
What kind of problem?
Overestimating the value of actions. Sometimes the AI gets overly optimistic about a move, so double DQN helps refine that.
And prioritized experience replay? That's interesting.
Yeah, imagine a lot of experience. Prioritized experience replay means the AI focuses on the tough decisions, where it was unsure of the best action. It helps focus learning on the less certain situations where it learns faster.
So, these techniques are important for other deep reinforcement learning. Why is that?
They're building blocks for more sophisticated methods. The techniques we discuss, like these value-based methods, are important to building models, and learning critics are crucial in actor-critic approaches. There's a lot more to discover.
Wow, there's a lot going on. And the rainbow algorithm? I've heard of it. Is it just a culmination of these?
Exactly. It's a powerful algorithm that combines many of the enhancements we've discussed plus others not in this book. It's a great illustration of how building upon existing work leads to better solutions.
Why should listeners try to implement these improvements?
Learning these methods really broadens your understanding of deep reinforcement learning. You'll see how you can combine them and improve models, leading to applications in everything from robotics to gaming. The experience is invaluable.
Thanks, Samuel. That really helps. So, reinforce VPG. They seem like different ways to optimize policies. Can you unpack the key differences?
Reinforce is a basic policy gradient method. It directly learns the policy using just the actual returns. That's kinda like trying to learn driving by only looking at how well you did on a single trip.
Right, a single episode. High variance though, right?
Exactly. VPG improves on that by adding a baseline value function. This baseline helps to smooth out the learning process.
So, you use the baseline to reduce variance?
Yeah, it's like having a reference point for your performance. This reduces the noise in the learning signal. Still, VPG isn't quite an actor-critic method.
Why not?
It uses the value function as a baseline, not a critic. It doesn't use the value function for bootstrapping. Imagine you're learning a new skill. VPG is like having a coach tell you if you're doing well but not using prior knowledge of the skill to improve your next attempt.
Interesting. So, bootstrapping is key to actor-critic methods?
Absolutely. They use the estimated value function to predict future rewards. That's like using past experience to predict how well you might do.
So, A3C, J, and A2C are all actor-critic?
Yes, these methods use bootstrapping. A 3C uses n-step returns, which gives you a better sense of long-term consequences.
GA uses lambda returns. That sounds similar.
It is. GA blends past and future rewards to have less variance than MC and better than just immediate rewards. A 2C uses synchronous updates.
Synchronicity? How does that work?
Imagine multiple learners working together. They all update their models in sync. It's faster because of teamwork but less flexible.
So, A3C especially is faster for CPUs. Why the difference?
Well, A3CS a parallel approach. It breaks down the learning across multiple agents or processes, working on different parts of the problem concurrently. This speedup for CPUs is crucial for environments where GPU access is limited.
So, we've talked about A3C, GA, and A2C. But these actor-critic methods aren't all created equal, right?
Exactly. While they use actor-critic structures, they don't use the critic in the same way. Other methods, like DDPG and TD3, are often categorized as actor-critic, but they're actually better understood as value-based methods for continuous action spaces.
Continuous action spaces? Can you elaborate?
Sure. Imagine controlling a robot arm. The robot arm can move in a continuous range of angles, not just discrete positions. DDPG and TD3 excel at those types of problems. They're really good at handling complex, continuous movements.
So, DDPG and TD3 are state-of-the-art, even if they aren't strictly actor-critic?
Yeah, and that's important. The classification matters less than their actual performance. They can solve these problems really well.
But they're limited to continuous action spaces?
Right. They can handle high-dimensional actions, but they must be continuous. A 3C, on the other hand, can handle both continuous and discrete actions.
Okay, so what about SAC?
SAC is a different beast entirely. It builds on some ideas from DDPG and TD3 but takes a different approach.
How so?
It's an entropy maximization method. It doesn't just try to maximize the reward, it also tries to maximize the randomness or exploration in the agent's policy.
That sounds interesting. Why is that useful?
It helps prevent the agent from getting stuck in local optima. It's like encouraging the agent to try different things. It's more exploratory, which often leads to better results in the long run. It's a promising method.
And PPO?
PPO, or proximal policy optimization, is another actor-critic method, and it's really cool because it's built on similar ideas to a 3C in terms of code reuse.
What's the key difference?
PPO updates the policy incrementally, ensuring that the updates don't change the policy too much. Think of it as a more conservative approach to policy optimization.
A more conservative approach. Why is that beneficial?
It's more stable, avoids drastic changes, and generally makes the training more robust. And it works well with both continuous and discrete action spaces, like a 3C.
So, these methods are building blocks. Is there any sense to understanding them together?
Absolutely. These are fundamental methods. Many newer algorithms stem from these foundational methods, with some exceptions like model-based deep reinforcement learning methods and derivative-free optimization methods.
So, a deeper understanding of these foundational techniques is key to understanding modern deep reinforcement learning. So, Samuel, you mentioned DRL algorithms. Reinforce, A3C, DQN. What's the deal with all these acronyms?
Yeah, it's a jungle out there. These are different approaches to training AI agents to make decisions. Think of it like teaching a robot to play a game. Each algorithm uses a different strategy.
Like different game strategies? Explain reinforce.
Reinforce is a basic policy-based method. It learns by adjusting its actions based on how well they perform. It's like trial and error, but with feedback.
Okay, so it keeps trying different actions and
adjusts the probabilities of those actions. The better the action, the higher the probability. It's relatively simple to understand, but can be tricky to implement.
Any others? A 3C, for example?
A 3C is an improvement, using multiple agents to train more efficiently. It uses asynchronous learning, running multiple learners on the same environment at the same time.
That sounds more powerful. Why might you use DQN over reinforce?
DQN is value-based. Instead of directly adjusting probabilities, it learns a value function to estimate the long-term reward of different actions. More stable.
So, it predicts outcomes instead of reacting directly? Why is that important?
Predicting outcomes allows for more advanced strategies. It's a more sophisticated approach, often leading to better results.
And DDPG?
DDPG uses a deep neural network to approximate both the policy and the value function. Crucially, it combines actor, policy, and critic value networks, making it more sophisticated and often more efficient in complex environments.
So, TD3, a 2C, PPO? What's the different take on these?
TD3 is an improvement on DDPG. A 2C and PPO are also policy-based, but more modern and efficient. They handle the exploration-exploitation dilemma better, finding a balance between exploring new actions and exploiting known successful actions more effectively.
An SAC? That's a whole other category, right?
Yeah, SAC is a more advanced policy-based method. It uses a technique called entropy maximization to encourage exploration. In essence, it makes sure that the robot keeps trying new things, preventing it from getting stuck in local optima and finding truly optimal choices.
So, a lot of these have nuances, like what are some of the pitfalls to be aware of when using these algorithms?
Choosing the wrong algorithm for a specific task is a big one. Understanding the environment's dynamics is crucial. If you don't understand what you're trying to optimize, you could miss the key components. Overfitting is also a risk, especially with the deep learning elements. The complexity also raises questions about interpretability. You're not always sure why the robot is doing what it does.
Very good, Samuel. Lots to think about. So, model-based deep reinforcement learning, right? How does it differ from other approaches?
Well, it builds on the idea of modeling. Instead of just reacting to experiences, it learns a model of the environment.
Like a simulation?
Exactly. It learns the rules of the game, so to speak. The transition probabilities, the rewards.
And then uses that model?
Yep, for decision-making. It's like having a virtual copy of the environment.
How's that more efficient? Learning a model sounds like more work.
It is, but it's efficient in terms of samples. Imagine trying to learn something from just doing it, trial and error.
Yeah, lots of steps.
Using a model means you can plan your actions, test different strategies in the simulation, all without directly experiencing them in the real environment.
So, more experimentation, less risk?
That's right. It's less reliant on actually trying every possible action.
Interesting. What are some practical applications?
Self-driving cars, robotics, game playing, any system where you want to learn to act optimally in a complex environment.
I see. Are there any drawbacks?
Well, building the model can be tricky. You need to make sure your model accurately reflects the real environment.
So if the model is wrong?
Your learning might be inaccurate, or worse, your actions might be unsafe or even harmful in the real environment.
So, careful validation is key.
Definitely. And like any reinforcement learning, the reward function is crucial. If the model is good but the reward is not properly defined, the outcome might be different from expected.
Makes sense. Thanks, Samuel. So, Samuel, you've touched on model-based RL. Tell us more about its advantages.
Well, it's about learning a model of the environment. Imagine an arm reaching for an object.
Right.
A model can learn how the environment reacts. This is super helpful for transfer learning.
Transfer learning?
Yeah, if the robot learns how the environment reacts to movements, it's easier to pick up the object later.
So, that's kind of like a playbook, right?
Exactly. Learning the dynamics is key. Reward functions aren't always transferable.
Interesting. Any other upsides?
Model learning is often more stable than pure RL. Plus, you can use algorithms for planning.
Like what?
Trajectory optimization, model predictive control, or even Monte Carlo tree search.
Wow, that's a lot more structure.
And you learn more from the environment, making decisions better.
So, if a robot figures out how to pick things up,
it learns how to pour too, potentially.
That sounds great. But downsides?
Model-based learning is computationally expensive.
More expensive than standard RL?
You're learning a model plus a policy or value function, all at once. Plus, model error can be problematic.
So the model is inaccurate?
Yes, and that compounding error could make the algorithm impractical.
Makes sense. Anything else?
Not all environment dynamics are useful to the policy. Think pouring. Learning fluid dynamics is overkill for picking up a cup.
So, sometimes learning the entire environment is unnecessary?
Precisely. Learning the policy directly is often simpler.
Okay. And deep learning? What's the deal?
Deep learning models are data-hungry. Model uncertainty is hard to estimate in them, which means long-term predictions could be garbage.
Garbage predictions?
Yeah, especially with neural nets. So the sample efficiency claim,
It's questionable?
yeah. You might need more data to build a useful model than you do for learning directly.
So, sometimes model-free is the way to go?
It depends. If you have a pre-existing model for something else, it can be reused. And sometimes shallow models are more effective than complex ones.
So, Samuel, derivative-free optimization. Sounds intriguing. Why the detour from gradient descent?
Well, Alfred, gradient descent is great, but it has limitations. Imagine a function with lots of bumps and valleys.
Like a roller coaster?
Exactly. Gradient descent can get stuck in a local minimum, missing the true global minimum.
So, derivative-free methods avoid those traps?
Precisely. They don't rely on gradients. Think of it as blindly searching for the lowest point, without needing to know the slope.
Blindly searching? That sounds inefficient.
It can be. But in situations with complex functions, like those in deep reinforcement learning, it can be surprisingly effective.
Like which situations?
Functions that are discrete, discontinuous, or have multiple local optima. Imagine training a reinforcement learning agent in a game where certain actions create unpredictable changes in the environment.
So these methods work well in uncertain environments?
Yes. They're also handy for situations where calculating gradients is difficult or impossible.
How do these methods work practically?
They might use methods like genetic algorithms or evolution strategies. They start with a population of possible solutions, and they evolve these solutions over many iterations.
Evolving solutions like in nature?
Yep. Each iteration, the solutions that performed better are kept, and the less effective ones are discarded. This process repeats until a satisfactory solution is found.
So, parallelization is key?
Absolutely. You can run these simulations on hundreds, even thousands, of processors simultaneously, making it incredibly fast.
But that comes with a trade-off?
They can be sample inefficient. You might need many more evaluations of the function than with gradient-based methods. Also, they don't exploit the structure of the problem, like the sequential nature of reinforcement learning. That's often important information for optimization.
So, it's not a silver bullet?
No, but it's a powerful tool for certain optimization problems. Gradient-based methods are still dominant in many cases though. Finding the right tool depends on the function and the problem.
Thanks, Samuel. That's a great overview of derivative-free methods. Okay, Samuel, so we've covered deep reinforcement learning. Now, you're talking about advanced concepts needed for AGI. What exactly does AGI mean?
Yeah, AGI is artificial general intelligence. It's the ultimate goal in AI. Think of it as creating machines with human-level cognitive abilities. Not just narrow tasks, but the ability to learn, adapt, and solve problems across a wide range of domains.
So, more than just playing chess really well.
Exactly. Right now, AI excels at specific tasks, like image recognition. But AGI would be way more general, like us.
What kind of traits do these hypothetical AGI agents need?
Well, they need more than just raw processing power. They need a level of common sense, for instance. Understanding that a hammer is used for driving nails, that sort of thing.
Common sense? Sounds almost philosophical. Can you give me an example?
Sure. Imagine an AI needs to figure out how to get to a destination. A narrow AI might just follow instructions. An AGI, on the other hand, could understand context. The roads are closed, the traffic is heavy, and use its knowledge to reroute, not just follow the instructions. It's like general problem solving.
Okay, so it's about adaptability, beyond just instructions.
Exactly. And it's crucial for unforeseen situations, new problems, not just those for which we've given it the parameters or instructions.
Right. So, what are other key traits? You mentioned it touches upon aspects beyond immediate tasks?
Yes. AGI needs to reason. Deduce conclusions based on evidence and not just react to inputs. And it needs to learn from experience, not just training data. That's a key component.
Learning from experience, so it's learning over a long period.
Exactly. It's continuous learning. Like a child learning about the world.
So, can you give a counterexample of where current AI falls short?
Absolutely. A narrow AI trained to identify cats in images might struggle to understand that a furry animal on a street could be a dog, not just a cat. It lacks the broader understanding.
Intriguing. It's not just about memorizing, but understanding the context, the relationship between objects, right?
Exactly. It's more nuanced than just recognizing patterns. It's about grasping the wider concept and making logical connections. It's a massive leap forward, but one we need to consider.
Okay, Samuel, AGI. What exactly is it?
Well, AGI, Artificial General Intelligence, aims for a computer program that demonstrates general intelligence.
General intelligence? Like human intelligence?
Exactly. The ability to combine different thinking skills, to solve novel problems.
So, AlphaZero, OpenAI 5, AlphaStar, are they AGI?
Not yet, I'd say. They're impressive, they can learn a lot of things. But they're really good at what they are trained on. Like a DQN agent trained for Pong, it's superhuman at Pong, but totally clueless about Breakout.
Why is that? It sounds like they're not flexible.
They're great at specific tasks, but transfer learning is a problem. You need massive training data to master a new task. Humans don't.
So, we're saying AGI is more about transfer learning?
More than that. It's also about adaptability. Humans can learn new games, new concepts, much faster than these algorithms. Learning to play Pong and Breakout are similar enough. The algorithms need much more training.
Is it just the training data then? Or is there something else missing?
Well, it's not just data. It's about general problem solving. And I think it's that very generality that's missing. AlphaZero is good at board games, but it won't clean your kitchen.
Interesting. So, there's a difference in the goals too, right?
Definitely. Some want AGI to automate tasks. Others see it as a way to understand human intelligence itself.
So, even researchers have different approaches. That's important.
Absolutely. Some want AI for practical use, others are interested in the fundamental nature of intelligence. And that's a crucial aspect.
Thanks, Samuel. That makes sense. So, we're a long way from AGI, but hopefully we'll get there. So, Samuel, you're saying reinforcement learning agents could learn without explicit rewards?
Yeah, Alfred, it's a really fascinating area. We usually give agents a reward function, like, get to the goal, plus 10 points. But recent research is questioning that.
But, how do you even define a goal without a reward?
Exactly. It's tricky. Think about a baby learning. They don't get a good job for every correct action. They learn by exploring, by trial and error. It's largely unsupervised.
So, no teacher, no grades?
Exactly. The agent is basically figuring things out on its own. It's a bit like figuring out the rules of a game without anyone telling you.
So, how does this relate to human-like AI?
Well, it might be a key to building truly general AI. Our rewards are often very narrow: career success, a good grade, but life's goals aren't always clear.
What are the potential pitfalls? If we don't define the goal explicitly, how do we make sure the AI aligns with our values?
That's a huge concern. How do we ensure the AI's goals match human needs? It's a major question that needs careful consideration. Giving AI complete autonomy is a huge risk.
So, you're saying it's like unleashing a very powerful, possibly unpredictable force?
Well, exactly. It opens a Pandora's box,
So, where does this research stand right now? Is it just theoretical, or are there practical applications?
It's still pretty early. We have proof-of-concept systems, but practical applications are nascent. Still, a lot of potential to uncover in this space.
What about the ethical implications? What are the concerns with these reward-free approaches?
Absolutely, that's a key concern. Unforeseen consequences are a possibility. Imagine an AI aiming for an objective we haven't even considered yet.
Is there a way to, introduce constraints to these reward-free approaches so the goals are within bounds?
Right, constraints are a very important way to think about these issues. It's about guiding exploration, not directing it completely. There are possible approaches, but they're still under active research.
So, Samuel, inverse reinforcement learning, it sounds like a way to learn without explicit rewards, right?
Yeah, exactly. It's like, trying to figure out what someone wants by watching them.
So, we're not just mimicking their actions?
No, we're trying to understand their goals, their motivations, the why behind their actions.
Cool. And how does that help us learn policies?
Well, if you know why someone does something, you can build a reward function, like a human playing a game. If you see them always going for high-scoring combinations, you can infer a reward structure based on points.
So, the reward is inferred?
Exactly. Instead of being told good job, you scored 10 points, we figure that out from their actions.
And what about cases where the reward is complex?
Yeah, that's tricky. The reward function might not be simple, like, just high score. It could depend on many factors, and we might need a lot of examples to figure it out.
But that inference step, isn't it kind of guesswork?
Well, it's inferring, not guessing. We're looking for patterns, for consistency. And often, a reward function is more concise than the perfect policy, like a recipe versus a finished dish.
So, apprenticeship learning is about combining those two?
Precisely. You learn the reward from demonstrations, then use that to learn a policy. It's like a shortcut.
A shortcut to a better policy?
Potentially. But it's not a guaranteed win. Sometimes, that inferred reward doesn't reflect real optimal behavior. The demonstration could be flawed or biased, leading to a suboptimal policy. There's the risk of biases from the demonstrations carrying over into the learned policy.
Sounds tricky. So, what's the trade-off?
You might get a good starting point quickly, but it could be suboptimal if your inferences are wrong.
So, when is it actually useful then?
It's great for initializing agents when learning from scratch is too slow. Imagine a complicated game. Starting from a completely random approach would take ages. Learning from a human, even if not perfect, might give you a much faster learning trajectory. Plus, we can use it in multi-agent situations, predicting another agent's goals, which is really important for strategic games.
That makes sense. Any downsides?
Yeah, the inferred reward may not be true, and the human demonstrations may be imperfect or biased, potentially leading to a suboptimal policy. So, you need to critically evaluate the demonstrations.
So, Samuel, you were saying that a simple simulator isn't enough for real-world transfer learning?
Exactly. Just a high-fidelity simulation isn't the key.
But why? Wouldn't a realistic simulation make the agent learn better for the real world?
Well, think of it like this, Alfred. A perfectly accurate sim, it's like one specific variation.
One specific variation. I see.
Real-world variability is huge. Domain randomization, that's the key. It's about creating lots of different scenarios.
So, you're saying diverse training data is better than a single perfect copy?
Precisely. The agent learns to adapt to different situations during training, not just one specific situation.
Makes sense. So, what's the downside to having lots of variability during training? Is it slower?
Potentially. But the payoff, in terms of generalization, is often worth it. An agent trained in randomized settings is better prepared for real-world surprises.
So, it's less brittle?
It's more robust. It's about generalizability, not just perfect replication.
That's fascinating. So, a flexible simulator allows for wider training scenarios.
Exactly. Sim-to-real transfer, it's not just about realism, it's about adaptability.
And this applies to robotics, right?
Definitely. Training a robot in a perfectly controlled environment can be misleading. It might not translate to the real world.
So, we're saying that a little bit of chaos, in a way, during training is crucial?
That's the essence of it. The agent has to learn to deal with the unexpected.
That's a game changer. Thanks, Samuel. Okay, Samuel, you were talking about multitask learning. Can you give us a basic idea of what that is?
Sure, Alfred. Multitask learning is like training a model on many different tasks at the same time. Instead of just learning one thing, it tackles several related problems.
So, it's learning multiple things at once? Is it like multitasking in a human context?
Not quite the same. Imagine teaching a robot to do multiple tasks. It's different from us. It's learning those tasks in parallel or sometimes in sequence.
So, what's the advantage? Why do this?
It often leads to better generalization. That means when you teach it something new, it can apply the learned concepts from other tasks. Think of it like building a strong foundation.
How so? Can you give an example?
Absolutely. Imagine a robot arm. Instead of learning just one task, say, picking up a specific object, it learns various tasks simultaneously, like picking up different objects or moving them to different positions. This gives the robot a broader understanding of movement and object manipulation. The robot learns general principles that apply to a wide range of situations.
So, it doesn't just memorize each task separately?
Exactly. The model creates a more robust understanding of the environment and the underlying principles. This understanding is then directly usable for new tasks or situations.
So, it's not just a matter of rote memorization, it's a deeper understanding?
Absolutely. It's about figuring out the fundamental principles involved, not just the specific actions. This is why the dynamics of an environment are key. Gravity, how an object moves, how forces interact. All of this is learned from the multiple tasks, so a new task can be learned faster and more effectively.
So if it's generalizing from different tasks, it's less likely to make mistakes that could derail a single task?
Potentially, yes. It could learn more robustly about these different aspects that work in parallel. It's all about generalizing and making sure that all the knowledge that it's accumulated from different task sets is not necessarily isolated.
So, if I've got this robot with 4 different effectors, it could still use this method, right? It doesn't have to be the same end effectors necessarily, right?
Correct. The tasks don't have to be identical. They just need to be related. Think of related tasks as different ways of achieving the same goal, like a robot with different arms picking up objects. It's about the common principles, not the exact actions.
Interesting. It sounds like there's a lot of potential for transferring this knowledge in lots of areas.
Absolutely. It could be useful in many areas beyond robotics, like image recognition, natural language processing, and maybe even medical diagnosis. The more related tasks you train on, the better it will generalize.
So, Samuel, you're talking about curriculum learning for multitask agents. Can you give us a simple example?
Sure, Alfred. Imagine training a robot to play video games.
Okay.
Starting with simple games, like Pong, and gradually increasing the difficulty.
Like more complex graphics, faster action?
Exactly. That's a curriculum. Start simple, then add more challenging elements.
So, how does the reward function play into this?
The reward function's key. Start with a clear, obvious reward for success in a simple task.
Like a bonus for scoring a point in Pong?
Yeah, high reward for clear wins. Then make the reward less obvious. Imagine winning a complex, high-stakes game. The reward is far less straightforward.
I see. So, we're making the environment progressively harder, but what's the benefit?
The agent learns more efficiently. It masters the basics first, building up to the complex tasks. It's like learning to ride a bike. You start with training wheels, right?
Definitely. You wouldn't try a triple axel on your first day of ice skating.
Exactly. It's smart engineering. You're not just throwing a complex problem at it.
So, are there any downsides? Could this lead to issues?
Potentially. If the curriculum isn't well designed, it could misdirect the learning. A poor curriculum might cause the agent to fail to grasp the underlying patterns needed for more advanced tasks.
So, planning a good curriculum is vital. What are some tips for building an effective one?
You need to understand the problem you're trying to solve. Think about the steps needed to master the task in a realistic order.
So my learning, what exactly is it? Learning to learn itself? That sounds pretty cool.
Yeah, it's a really fascinating area. Imagine, instead of teaching an agent how to do a task, we teach it how to learn.
So like a super learner?
Exactly. It uses experiences from tackling many different tasks to improve its own learning process. It's a bit like studying multiple subjects to become a better student overall.
So, we're not just programming specific behaviors, but
we're creating a system that gets better at learning itself. Instead of hand-coding every detail, it figures out how to learn efficiently.
And why is that better? Why not just keep hand coding?
Well, think about it. We're limited by how much we can code. Meta-learning lets the agent find its own optimal solutions. It's about efficiency. Hand coding is like memorizing every page of a textbook, while meta-learning is like understanding the core concepts and applying them.
So, it basically automates learning?
Exactly. It's like a self-improving learning process. And it opens up some incredible new possibilities. Like automatically discovering optimal neural network architectures. Imagine a neural network that designs itself.
Wow, that is mind-blowing. So, what does that even mean?
It means algorithms that can choose the best structure for a neural network. Instead of us guessing, the system finds the ideal architecture on its own. Think about the time and effort we save.
And what about optimization methods?
Similar. Meta-learning can find optimal ways to train networks. Instead of using standard methods, the agent adapts and finds the perfect approach for different situations. Imagine a learner who learns what method works best on a particular problem. It's a smart solution.
So, is this something that's in use today?
Not yet everywhere, but definitely emerging. It's a very active research area, and its implications are huge. It's not a magic bullet, though. There are still challenges to overcome, like ensuring the agent learns effectively and avoiding getting stuck in local optima.
So, challenges remain, but the potential is tremendous. Thanks for explaining meta-learning to me. So, Samuel, you were talking about multi-agent reinforcement learning. Sounds fascinating. Can you give us a basic overview?
Yeah, it's about learning when lots of agents are interacting. Imagine like a bunch of robots working together or competing. The challenge is, as one agent learns, the others change, right?
So, the learning environment keeps shifting?
Exactly. That makes it tough for any individual agent to keep learning effectively. It's non-stationary, like trying to learn a new dance routine while the music keeps changing.
Interesting. And what about cooperative multi-agent learning? How do agents learn to work together?
One cool approach is actor-critic methods. The critic looks at the whole picture, all the agent states.
So, a central system sees everything?
Exactly. It helps the agents learn to cooperate. Think of it like practice in a team sport. You practice with complete information, then use what you've learned in real games, with less information. It's like practicing a play in detail, then executing in a real game with limited visibility.
That's a good analogy. But how do you apply this to real-world situations?
Well, imagine a bunch of self-driving cars needing to coordinate traffic flow. The critic could see the full state of all vehicles' positions, speeds, etc. They learn how to cooperate to keep everything smooth.
Makes sense. So, hierarchical reinforcement learning is like multi-agent too?
Yep. You can think of different levels of agents, like in a company. Higher-level agents set the big goals, lower-level agents figure out the details.
Like a CEO setting strategy and department heads implementing it?
Exactly. Each level learns its own part, with the whole system rewarded by success.
And what about the adversarial side? Is it just about competition?
No, it's more about improvement. An adversary, even a previous version of the same agent, pushing against it, helps it learn better strategies. Think self-play, or tournaments where the best agents survive. It's like a continuous, challenging test.
So, it's not just about winning, it's about getting stronger.
Absolutely. It forces the system to adapt and improve constantly. It can be incredibly valuable for creating robust, adaptable systems. It's a natural form of stress testing, if you will.
Wow, that's a lot to take in. So, the constant changing environment in multi-agent settings is a big hurdle, but also a key to improvement?
It's a tricky balance, but also the catalyst for significant improvement. The core challenge of non-stationarity is overcome through smart learning approaches, which themselves are constantly being improved.
Makes complete sense, Samuel. Thanks for breaking it down. So, Samuel, you're saying RL algorithms are flexible? They can tackle any problem?
Yeah, almost any. The key is representing the problem as a Markov decision process, or MDP.
Okay, that's familiar. But translating real-world problems into MDPs? That's the challenge, right?
Absolutely. You need to define the states, the actions, and the rewards. It's like designing a map for the agent to navigate.
So, If I want to build an RL agent to trade stocks, that's possible?
Potentially. You define stock prices as states. Possible actions might be buying, selling, or holding. Rewards would be based on profit or loss.
But how do I create this environment? It's not like a pre-built game.
Exactly. That's where you learn from existing ones. Look at how Atari games or Mujo-ko simulations do it. They often use emulators or physics engines as their backend.
So, you're suggesting reverse engineering? Studying how these pre-built ones handle observations and actions?
Precisely. How do the observations, like images in Atari, flow from the emulator to the RL agent? How are actions passed back to the simulation? That pattern is common. Copy the design, adapt it to your environment.
And if I don't find a similar setup?
You build your own. For stock trading, you need an API for accessing market data. Create different environments, one for buying stocks, another for options, and so on.
Creating environments seems like a lot of work. Isn't there a risk of getting it wrong?
It is. That's why building custom environments isn't always straightforward. It's a lot like software development. But the reward for solving a problem, a novel market approach, can be very high.
So, if I'm a researcher and I have an idea for an innovative trading strategy,
you could use RL to explore these novel strategies. That would require creating a custom environment.
So, building a custom environment is not just for play, but it's crucial for research too.
Exactly, and if you create a useful environment, sharing it is helpful to the community.
Thanks, Samuel. This is super helpful. Now I have a better grasp on developing custom environments for RL agents. So, Samuel, you're saying we need to prioritize learning, but also contributing?
Yeah, exactly. It's a balance. Like, working out.
Right? You need to fuel your body.
And your mind. You can't just cram information.
Without giving it time to process.
Exactly. It's like trying to run a marathon with an empty tank.
So, what's a good way to balance that intake and output?
Well, find your drive first. What truly motivates you?
That's key.
Absolutely. If you're not driven, the learning's not gonna stick.
That makes sense. What about the constant distractions?
Yeah, that's huge. We're all bombarded. It's a battle for focus.
So, we need to consciously regain control?
Precisely. We need practice. Long stretches of focused work.
You mentioned rest too. Why is that important?
Because it lets your mind process everything. It's like letting the ideas percolate. Like baking a cake.
Ah, I see.
You gotta give it time to rise and form. Too much input, no time to rest, you become stale.
Okay. So, careful consideration of what we read and learn?
Yes, vital. Don't just gulp down everything.
And who we listen to?
Important. Their background, their expertise.
That makes a lot of sense. So, we should also be experimental?
Absolutely. Trying things out is important, even if they turn out to have been done before.
That's smart.
It's more valuable to move forward than to wait for a perfect moment.
And then, embracing the process itself?
Yeah. Your goals are a path. It's about the journey, not just the destination. Getting deep into the interesting questions.
So, it sounds like you're advising us to be passionate?
Yes. Focus on what you enjoy. And be okay with not knowing everything.
That's good advice. But, what if you get stuck? You hit a wall?
Ask questions. Don't be afraid.
I like that. Dumb questions?
No such thing. Every question is a clue. Keep asking.
Sounds good. Thanks, Samuel. So, Samuel, you've just finished this deep reinforcement learning book. Now what?
Gotta get out there, Alfred. This stuff is so cool.
Absolutely. So, you're suggesting like immediate action?
Yeah, exactly. Think about what's missing from the book. And how to build things.
That's great advice. Blog posts? Videos?
Totally. Maybe a blog post on reinforcement algorithms not covered in this book. Algorithms I find fascinating.
Interesting. Maybe some of the advanced stuff in the last chapters?
Exactly. Sharing insights on those advanced concepts. That's where the real learning happens,
Yeah, I see. So you're suggesting sharing your discoveries?
Yeah. Become part of the conversation. It's a community thing.
And that's important in this field?
Crucial. Learning from each other, sharing ideas, building better systems.
So you're talking practical application, building something?
Definitely. We can't just study these things. We need to build things to see how they function.
Smart. So, what kind of stuff would you want to dive into from that last chapter?
Well, maybe some of the newer approaches to dealing with exploration-exploitation trade-offs. That's often tricky.
Sounds deep. What are the common pitfalls in that area? So, Samuel, you've wrapped up this deep reinforcement learning book. How'd it go?
It went well, Alfred. I think the key takeaway is understanding the core concepts.
Absolutely. You laid out a definition of deep reinforcement learning. Can you quickly recap that for us?
Deep reinforcement learning is about creating computer programs that learn. Crucially, they learn by trial and error. And this feedback is sequential, not just random, but judged as they go along.
So, crucial for this kind of learning is the sequential feedback. What's the importance of that?
The sequential aspect is super important. Imagine training a robot. If the robot only gets feedback at the end, you might not know where the robot went wrong. You learn much faster if feedback is instantaneous and continuous.
Got it. And what about this sampled aspect?
The sampled part means the feedback isn't complete. It's often a snapshot in time. It's a very realistic learning process, as we often don't have complete knowledge of the system.
So, you're saying it's like trying to understand a complex system through experiments, rather than just through a full, detailed blueprint?
Exactly. We use samples, learn from those, and adjust.
That sounds remarkably like how we humans learn sometimes. You mentioned using words that were precise. Why is that so important in a definition?
Precision is key. The words help us understand what is distinct about deep reinforcement learning. Without that, it's just another AI approach.
Right. Now, you said you reviewed all the methods. What are some of the most important you covered?
Well, we covered the basics, like Q-learning and SURSA, and went all the way up to the very advanced models. It was a huge leap.
That's impressive. And did you touch upon where this field fits within the broader AI picture?
Definitely. Deep reinforcement learning is a crucial tool for building AI agents. It's a part of a bigger picture, and it's critical to understand its role.
That's very helpful. So, this book is complete. What's next? What do you hope people gain from it?
I want people to have a strong intuition for deep reinforcement learning, understand the methods, and know where to go next in this incredible field. Now, the ball is in their court.